The industry reached a widely publicized milestone, the 1 million token context window, carrying the promise of endless, seamless memory for language models. If we look purely at benchmarks, heavily resourced long-context models empirically outperform standard zero-shot retrieval augmented generation on average tasks. This chart shows the performance gap between long-context and RAG across frontier models, comparing the orange LC columns against the pink RAG indicators for GPT-4o, GPT 3.5 Turbo, and Gemini 1.5 Pro. But processing those massive windows creates a mathematical wall. The memory required to store the model's key value cache scales quadratically with every token added to the system. Feeding a full 1 million token sequence into a model pushes GPU memory requirements well beyond 200 gigabytes. Because of those hardware constraints, long-context models remain mathematically unviable for high-throughput or local deployments. The notion that RAG is obsolete remains a theoretical projection. Running true long-context applications requires massive physical infrastructure, restricting deployment to expensive, multi-GPU cloud data centers. Relying on those data centers imposes strict economic penalties. Query costs can exceed 10 cents per request, paired with significant latency delays for every round trip to the server. Contrast those constraints with the economics of local inference hardware. RAG compresses gigabytes of unstructured data into roughly 800 highly relevant tokens, functioning as an extreme context filter. This compression allows capable 8 to 12 billion parameter models to run entirely on standard 16 to 24 gigabyte consumer GPUs. Local deployment enabled by RAG yields two architectural advantages: strict data privacy guarantees and zero network latency. Hardware economics dictate that RAG persists as a mandatory bridging technology for all edge computing applications. Engineers rarely face a binary choice between standard RAG or full long context inference. Testing reveals that for over 60% of standard queries, the prediction accuracy of RAG and long context models is identical. To optimize this overlap, developers implement a self-routing architecture. The system attempts a low-cost RAG pass first, using a reflection token to verify if the answer exists. Only if the context is explicitly unanswerable does the system trigger a computationally expensive long context pass. This chart details the performance of this hybrid approach. The green self-route bar for the GPT-4o cluster closely matches the orange long context baseline. Dynamic routing slashes token costs by up to 65% while maintaining accuracy. System efficiency relies on knowing exactly when to spend compute. Passive retrieval is being replaced by Agentic RAG. These pipelines embed autonomous cognitive control flows directly into the generation process to evaluate their own data. Corrective RAG, or CRAG, serves as a safeguard against low-quality retrieval poisoning the language model's context window. CRAG utilizes a dedicated evaluation layer. A high-speed model scores retrieved documents against a strict internal relevance threshold before generation begins. For documents that pass the relevance threshold, a decomposition algorithm surgically extracts only the pertinent facts, discarding the surrounding noise. If internal documents fail that relevance check, the system initiates an autonomous fallback protocol. The pipeline redirects to an external web search to dynamically fill the knowledge gap in real time, preventing the model from halting. Agentic modularity shifts RAG from a passive script into a resilient, self-correcting research agent. Standard dense vector retrieval retains a critical flaw. It breaks down during complex, multi-document logical deductions. This chart illustrates why RAG fails on advanced datasets, specifically highlighting the blue columns representing multi-step logical failures in MusicQueue and HotpotQA. The architectural cause lies in how dense vectors operate. They map probabilistic semantic similarity, making them blind to actual logical relationships between discrete facts. To solve multi-hop queries for legal and technical applications, developers must deploy knowledge graphs and GraphRag. Instead of relying on proximity, this advanced method extracts entities and organizes the underlying data into a structured, highly interconnected relational network. During ingestion, GraphRag utilizes language models to extract specific entities and hard relationships, building a formal structural layer. Execution requires a dual-layer retrieval, fetching unstructured text via vector similarity while simultaneously traversing the graph to extract connected nodes. Comparing these methods highlights the superiority of relational logic for complex queries. GraphRag replaces blind vector proximity with strict relational determinism. Transitioning from theory to production reveals a final friction point. Hard-coding text prompts for these complex agentic pipelines is unsustainable. Developers use DSPy, an orchestration framework designed to separate pipeline logic from the language model itself. This code shows the syntax of an optimized programmatic orchestration environment. The MyPro v2 optimizer automatically compiles, evaluates, and optimizes RAG prompts against custom metrics to maximize factual grounding. But building dense indexes for terabytes of data remains a significant production bottleneck. The solution to index build latency is direct hardware acceleration. Engineers offload vector database index builds to the GPU using NVIDIA QVES, turning hours of CPU processing into seconds of GPU parallelization. The arrival of million-token context windows pushed RAG to evolve from a simple search tool into a highly optimized cognitive framework. By layering graph logic, agentic routing, and hardware acceleration, engineers can achieve data center-level reasoning capabilities at a fraction of the cost.